Hey guys, so when I posted the video about like upper triangular matrices, uh there's this lemma which I used, which I wanted to go back to. So let's see it. It says if K is a normal subgroup of G and H is a subgroup of G which contains K, then the following two conditions are equivalent. The first condition is that the subgroup H mod K is contained in the center of G mod K, and the other one is that the commutator of H and G is contained in K. And let's just see why this should be true. Well, starting with the left-hand side. Oh yeah, so a little h, the coset of H is in the center of G mod K for all H in H. If and only if, well, HK is in the center of G mod K, if and only if the commutator of HK with any GK is the identity of G mod K, so EK. Okay, well, the commutator of any H with any G is the identity if and only if the commutator subgroup generated by H, like H comma G, is a subgroup of K, which is the other condition that we stated, right? So that means that when we're checking if some sequence of subgroups is, a central series, we can really do it using this commutator condition. Okay. Also in this video, I wanted to just go over a few basic properties about commutator. So first, let's define the commutator of let's say G and H. It's just GH, G inverse, H inverse. And then, I need some more space here. I didn't plan things out. But now if you have a subset, like subsets X and Y, the commutator of them, the commutator subgroup of X comma Y is just the subgroup generated by the commutator of everything in X with everything in Y. Right? Okay. That's the commutator subgroup. And just a few basic properties. Let me start over with this further down. So yeah, some few basic properties about the commutator, which we'll need later, meaning on Thursday. Okay, we have that the commutator of X with Y is the inverse of the commutator of Y and X. I guess I might as well write this following the commutator of X and Y is the identity if and only if XY equals YX. Actually in general you have something like commutator of XY times YX equals XY. Okay, so this commutator, it kind of measures how far away it is from X communing with Y. Okay. We have more basic things I want to write down. Let's see. You can do all kinds of things, right? So if you want to know what is a commutator of XY with Z, that's almost like a product of commutators. It is X, Y, Z x inverse xz. Okay. So you kind of have like a almost like a distributive property of the commutator. There's something similar you can say if you switch, like if you do x with yz, there's something similar as an application, but I'll just leave that out. That's in the notes. But just as an application of this property, you have that commutator of x with y inverse times y inverse xy. Y is the identity. So you can write the commutator of x with y inverse in terms of commutator of x and y, and like you need to conjugate by y. Okay. And so just as an example, let's prove this one. And then we'll leave it there for now. Okay. So let's see. So we need to write a proof of, let me write it down again. X, Y, Z. And I will never ever remember this, but it is useful. Okay. Well, let's just work out both sides. This says proof of. Sorry that it looks weird. Okay, so we just expand both sides. On the left-hand side, this is xy z times xy inverse z inverse, which would be xyz, y inverse, x inverse, z inverse. Okay, now let's expand the right-hand side. We have x times commutator of y and z. We have y, z, y inverse, z inverse, x inverse times commutator of xz. Okay. So that's the right-hand side all written out. And let's just, we right away we see we can cancel x inverse x. So let's, here you get equals x, y, z. Y inverse, z inverse, z, x inverse, z inverse. And now we can cancel z inverse z. Same thing. Okay. So let's stop there. Thanks for watching.